Hi everyone, welcome to the revision of the artificial photosynthesis patch in the PicNX module. I'd like to give you a little bit of a revision of what I've done in the lecture and hopefully answer any questions that you might have. In particular, what do I need to know for the exam questions? If you have any questions that aren't answered in the slides, feel free to drop me an email. I'll be happy to help you, especially regarding the exam questions that I put up, like the practice exam questions or the workshops. Last time there was quite a bit of mistakes in there, so if you're uncertain about anything, just email me and I'm happy to help. Right, so introduction to solar fuels or artificial photosynthesis. What is it and why are we interested in doing it? Very straightforward. Solar fuels is the storage of solar energy in bonds, in chemical bonds, and we want to store energy because renewable energy is intermittent. So the sun doesn't shine at night, but at night we need energy to turn on the light in our house. We don't need much heat in winter, but the sun shines less in winter, and so we need to overcome this mismatch of supply and demand for renewable energy. That's why we need to store energy, for example, in some sort of tank, as shown here in these Royal Society slides. You make solar fuel, you store it in a tank, and at night, when the sun doesn't shine, you take the fuel out of the tank and power your house or your petrol station. Why fuels? Why not batteries? Plainly because the demand is there for fuels, not for batteries, not for electricity. Electricity is only a minor portion of the global energy consumption. So if we want to make an impact, we need to supply renewable fuels. Fuels are useful because they don't weigh very much, they are not very large, so it's easy to transport energy and store it in the form of fuels, much more convenient than batteries. And if we are thinking about solar fuels, we need to consider how available are the elements that we need to produce and use that fuel. So if we use catalysts, these should be based on earth-abundant elements. So not platinum and rhodium, but they should be based on iron, cobalt, not even cobalt, or iron, nickel, oxygen, silicon, and not platinum. That's the point. And in addition, the fuel itself should be made from abundant elements. So if we want to do this on a large scale, we should not make a fuel that's based on bismuth, because there isn't that much around, right? That's why we want to use an abundant element. And the most abundant element is hydrogen, and that's why one of the fuels that are being discussed is hydrogen fuel. You can make hydrogen fuel from water splitting, from solar water splitting. So you take water and you split this into hydrogen and oxygen, and the overall energy difference or potential difference between those two sides of the redox reaction is 1.23 volts. You can split the reaction into two half reactions. One is the proton reduction reaction or hydrogen evolution reaction, where two protons react with two electrons to give you one molecule of hydrogen, and the standard potential is 0 volts versus NHE. The other half reaction is the water oxidation reaction or oxygen evolution reaction, in which water gives away 4 electrons to give you a molecule of oxygen and 4 protons, and the standard potential for this half reaction is plus 1.23 volts versus energy. So the minimum energy required for this overall process is 1.23 volts. If you want to drive this with light, that light needs to supply energy of 1.23 electron volts. But these potentials are only under standard conditions, which means pH 0 and 1 bar. If we are changing these conditions, the potentials are also going to change. And this is something you can calculate with a Nernst equation, which is shown here for the hydrogen evolution reaction. So the actual potential at which it happens depends on the standard potential plus this term that accounts for the temperature, the number of electrons exchanged, and the concentration of protons and the pressure of hydrogen. If you put everything to standard, so 1 bar hydrogen, 25 degrees C, and so on, you end up with this expression, which is very easy to use. So the hydrogen evolution potential is minus 0.059 volts times pH. And if you plot this, you can see it's shown here on the right. At pH 0, standard potential is 0 volts. And if you increase the pH, you have to go more negative. It's plainly because if you become more basic, there are fewer protons around, so it's more difficult to reduce protons because there are just fewer available. The opposite holds true for oxygen evolution. I'm not going to go through this again, but it's the same thing. You end up with an expression where the potential is 1.23 volts minus 0.059 volts times pH. So if you increase the pH, the oxygen evolution becomes easier, so closer to zero, but the difference between the two still remains the same. It's still 1.23 volts potential difference, but the individual reactions become easier or harder depending on which way you go on the pH scale. And finally, if you do all this, you obviously have to keep an eye out on the efficiency of your process, and the most universal way to measure that is the solar to hydrogen efficiency, STH, which is the fraction of output energy versus input energy, so the energy of your fuel and the energy you put in, for example, as sunlight. And the way in which you calculate the output or the input energy depends on the system that you are using. There are three main systems by which artificial photosynthesis is normally done. One is PV electrolysis, so it's the combination of a solar panel with an electrolyzer. Second one is photoelectrochemistry. You have a photoelectrode integrated into an electrolyzer, or you have photocatalysis, where everything is integrated into one particle. I'm going to go through these now relatively briefly, one by one. But universal to all three of them is the fact that we want to use sunlight to drive the process, hence the name solar fuels or photosynthesis. And so to do that, we need to know the solar spectrum, which is shown here on the bottom right. The blue trace here on the outside, that is a spectrum you'd expect from a black body at 5,800 Kelvin. And so you can see that the solar spectrum, which is the red trace on the outside of the atmosphere, is very similar to that black body irradiation. So you've got UV, hard UV in that range, and you've got a maximum around 400, 500 nanometers, and then you've got a long tail in the IR. If you look at the black curve, which is the solar spectrum as it hits the surface of the air, so after the light is passed through the atmosphere, you can see there are a few sections missing. So there is light intensity missing in the hard UV, there's some visible light missing, and there are bits missing in the IR regime. And this is due to the fact that some of the light is being absorbed by ozone, that's in the UV, by O2, that's some UV and some visible light, and CO2 and water, that's in the IR. Plus there's some scatter and dust that also absorbs some light, so the intensity overall is lower. Normally, it's assumed that the standard light intensity is 1,000 watts per square meter. That's the universally agreed standard for one sun energy. And if we think about, again, the potential required to split water, this is indicated here, 1.23 electron volts, corresponds to around 1,000 nanometers. So all the photons of shorter wavelength, so all this is light that we could potentially use to split water if we are very, very efficient. Right, before I go into detail of the artificial systems, I just want to briefly recap on the natural photosynthesis. Natural photosynthesis is quite a complex multi-component system, but it has some interesting features that are a good inspiration for artificial photosynthesis. Main thing is we've got two light absorbing centers, PS1, photosystem 1, and PS2, photosystem 2. And what happens is when you take your photosynthetic organism and you shine light on it, you excite PS2, which then oxidizes water, passes on the electrons via the plastoquinone pool to cytochrome B. From there, electrons are passed on via plastocyanin to photosystem 1, where the electrons undergo a second excitation, after which they kind of are secreted from the thylakoid into the stroma, passed on to ferredoxine, and then from there they are passed on to ferredoxine NADH reductase, for example, to make NADH, and the NADH is then distributed to do all sorts of different reactions, fixing nitrogen by nitrogenase, producing hydrogen by hydrogenase, fixing carbon by other enzymes, and the whole cascade. I'm not going to talk about this, but in general, This is the photosynthesis part, and everything else is dark reactions that are happening afterwards. The key thing is we have two separate light excitations, and we have a mediating system in between them. And I'm going to go through the energy balance of this in a little bit later. The magic really happens at photosystem 2. That's where the water oxidation reaction happens. And it's a very complex protein, but at the core of it is what's shown here on the right. You've got a pair of chlorophylls, which is called the special pair, and this is where the excitation happens. But before that, on the outside, sort of on the left and right in this schematic, you've got the antenna system. So it's a huge amount of chlorophyll moieties, and these absorb light very well and funnel it through into the special pair, where then you have an increased light absorption, increased charge separation. And that charge separation is then dissipated by electrons from the special pair, P680, being transferred first to thiophytin, from thiophytin to quinone A, from quinone A to quinone B, and then from quinone B, which diffuses out, so kind of floats out of the protein up to cytochrome B. Now the key in this is that you spatially separate the charges. You can see distances are here shown in angstroms. You take the charges further and further away from P680, which means you are decreasing the likelihood of any recombination, so the efficiency of this is very, very high. The holes remaining at P680 are quenched from tyrosine Z, which in turn is quenched then from the OEC, the oxygen evolving complex, which is the actual active site for water oxidation. OEC is able to store 4 holes, and these are the 4 holes needed to oxidize water to oxygen. And by doing it in 4 individual steps, it avoids any high energy intermediates to make this process very efficient. And it also manages to do all this by using low energy photons, of which there are most available in the solar spectrum. This is the mechanism by which it works, the so-called Koch cycle. If we start at the ground state, so the S0 state is a fully reduced OEC. You've got this manganese calcium oxygen cluster here, so 4 manganese atoms shown in pink and purple, and 1 calcium atom. And in the S0 state, 3 of the manganese atoms, the pink ones, are in oxidation state +3, and 1 is in +4 state. And so as you excite P680 and extract electrons, these manganese atoms get successively oxidized. So a second one gets oxidized. We've got 2 +4s. In the S2 state, we got 3 +4s. In the S3 state, we got all 4 oxidized. And then when you do a final oxidation, you are liberating oxygen from that cluster. I'm not going to go through the detail of the mechanism. I've done that in the actual lecture. You can look at this again to understand every single step individually. The main take-home message is that you do all these steps individually. So you do 4 individual steps with small energy. Many of these are proton-coupled electron transfer steps. So you are transferring a proton and an electron at the same time. So you don't change the charge of the system overall. You also don't change the geometry very much. So you have a very low reorganization energy, which makes this process fairly efficient. And finally, what happens is you are pre-aligning 2 oxygen atoms in close proximity, which means that the step from going to here to there to then O2 is also energetically not very difficult. So you are keeping the energy barriers to an absolute minimum, again, making the process very efficient. This is the overall energy diagram of the natural photosynthesis, so at least the light reaction. I'm not going to go through this again, but the main thing is you've got 2 light absorptions, PS2 and PS1. So you excite PS2, the holes get quenched by water oxidation, and the electrons then drop down this cascade of the different cofactors until they end up in P700, which is the light absorbing unit of PS1. They get excited again, and they drop down the cascade again before they actually make the final reduction product, NADPH. So we are creating a large potential difference, and then we are dropping it down to almost the same level, and then we are creating again a large potential difference, and we are dropping it down again. It sounds bizarre, but this is really good. although we are wasting a lot of the energy that we're putting into the system, we are rapidly separating the charges, and so we are preventing recombination. So there's a trade-off between being energy efficient, because we are losing a lot of this energy, and being quantum efficient, because we are able to conserve all those excited electrons and prevent recombination, but at the cost of losing energy. That's why two excitations are necessary to drive the overall process of NADPH formation and water oxidation, even though the overall energy difference between the two, if you look at it, is about the same as the first excitation. So we wouldn't need two excitation steps if we hadn't done that charge separation that costs us some energy. The charge separation helps us to make this process very efficient in terms of photons that we are actually using. Right, enough bio. Let's go to synthetic systems. They are a bit simpler. Let's start with PV electrolysis, which is the most simple and straightforward system. You hook up a PV panel with an electrolyzer. That's very easy to do. So you excite your PV panel, which normally is a semiconductor. So you do electron-hole pair formation in that PV panel. And the electrons and holes travel through cables to your electrodes and oxidize water and reduce protons to hydrogen. You are separating the two half reactions by a membrane so that you don't have a mixing of the two products, which would lower your efficiency and give you explosive mixtures. And there's your system for splitting water. The advantage is that works pretty well. It's all established technology, mature technology. You can buy electrolyzer, you can buy a solar panel. The disadvantage is you have many different steps, so you lose efficiency at every step. So the efficiency of these systems is not particularly high. How do we measure efficiency? Again, it's output energy divided by input energy. In this case, we simply take the efficiency of the PV panel, so here written as eta PV, times the efficiency of the electrolysis, so eta electrolysis. Eta PV is basically power output divided by the solar input. You can get this from the box when you buy a solar panel, or you can measure it. And the eta electrolysis is composed of two components. One is the voltage efficiency. So how much more voltage are we applying than the standard 1.23 volts? So for example, if we apply 2.46 volts, our efficiency is 50%. And the second is the Faradaic efficiency. So how many of the electrons that we pass through our cell are actually used to split water. So we divide the number or the moles of products generated by the moles of charge that we put in. There's this equation. I'm not going to talk through it, but this gives you an efficiency. So for example, if you have a lot of crossover and you have a lot of oxygen reduction happening, those electrons aren't used to make hydrogen. They are used to make water, which doesn't count for your products. So your Faradaic efficiency will go down. The voltage depends largely on the overpotential and the ohmic drop. I've talked about this in the lecture a little bit. If you have a large resistance across the membrane, you have to apply an extra voltage just to make those counter ions diffuse through the cell. And the larger your current density, the higher the ohmic drop. So if you increase the current density, your ohmic drop increases and you have to apply more and more voltage and your efficiency goes down. Additionally, overpotential depends on your catalyst. If you have a poor catalyst, you have to apply a lot of extra voltage. If you have a good catalyst, you don't need to apply that much voltage. This is expressed in the Tafel slope, which shows you how much the current increases if you increase the overpotential. There are three main types of electrolyzers. The most established one is the alkaline electrolyzer, which uses KOH, aqueous KOH as the electrolyte, and the two half reactions are separated by a diaphragm that conducts OH ions. It's fairly low cost because the catalysts that you use are based on fairly abundant metals, so iron oxide, nickel oxide, cobalt oxide, relatively affordable. The diaphragm is not expensive, but it has a high resistance. You can't pressurize it, and it's quite leaky, so you get a fairly low efficiency. So alkaline electrolyzers are established. You can buy them. They work. They aren't super efficient, but they are fairly affordable. A more advanced type is the PEM electrolyzer, polymer electrolyte electrolyzer. The main thing here is that you don't have a diaphragm anymore, you have a proton conducting membrane that separates the half reactions. Typically it's a solid acid such as Nafion, but because it's a solid acid, it only works under acidic conditions. That means you need to have a catalyst that's tolerant to highly acidic conditions, for example platinum, which makes the whole system quite expensive, plus the membrane is also expensive and usually doesn't last very long. But membranes are good. They separate the reactions quite well, much better than diaphragm. They have a low resistance, so you get higher current densities, and they have less crossover. You can also pressurize them, which actually allows you to form pressurized hydrogen directly from a fuel cell, which is a big advantage. You can also buy these. They are off the shelf now. They work quite well, have a good lifetime, but they're expensive to buy. The final type is the solid oxide electrolyzer or high temperature electrolyzer. Instead of a ion exchange membrane, in this case, they use a solid oxide conductor, typically a ceramic material, that separates the half reaction and works by having conductivity for oxide ions. Obviously, you get solid conductivity only at high temperatures, so these electrolyzers work at temperatures typically around 800 degrees C. They separate the half reactions very, very well. They're also very efficient. They can live with using inexpensive catalysts such as nickel and molybdenum. But because they require high temperatures, you need to put in extra energy to heat them, and they don't last very long because they degrade. You also have to use materials that are able to cope with high temperatures. So they are still sort of experimental, but expected to be the next big thing in a few years, maybe a commercial scale. The second technology is photoelectrochemistry. I didn't talk about this very much in the lecture due to time constraints, so I will limit this to just one slide. Basically, it's integrating the solar panel into the electrolyzer. So one of your electrodes is now light absorbing. It's called a photoelectrode, in which the charge separation occurs, and the electrons from that photoanode are transferred through the cable to the counter cathode where hydrogen evolution occurs. Everything else is pretty much the same. Big difference now is that the light absorber is immersed in solution, and the whole thing has to be transparent because light needs to go through the cell to reach your photoelectrode. The advantage is you have fewer bits, there's fewer chances of efficiency losses, so overall it should be more efficient. But because you have to immerse your electrode into the potentially quite acidic solution, your photoelectrode often degrades. There aren't any very stable, very good ones known at the moment, so they decompose over time. Plus, it has to be transparent, so light hits your membrane. Membranes are made of plastics. Plastics don't like light, so they will degrade. So overall, they don't last very long. So it's a very nice technology. In principle, it could be cheap and efficient, but it's just not there yet at the moment. The final technology I talked about, and I've probably talked about most, is photocatalysis. That's the field I work in personally, so obviously I know most about it. In this case, you have the charge separation, both halves happening in the catalyst. So you have a photocatalyst where you get electrons and holes, and both of these react directly in the photocatalyst on the photocatalyst surface to reduce protons and oxidize water to oxygen. It's a very simple system. It's all integrated into one particle, makes it cheap, makes it easy to use, easy to handle, has a large surface area, reactions are usually fast. But because everything happens in one place, it's very difficult to tune parts of these reactions individually, because if you change one thing, you're probably changing also the rest, which makes optimization quite difficult. The efficiency is typically quite low because everything is in one pot, which means that you form hydrogen and oxygen in the same pot, and so you have reverse reactions. So one of the challenges is the reverse reaction. So hydrogen plus oxygen recombine to give you water, which then means you are losing your photons because you're losing your product. Second thing, which happens quite often with photocatalysis, is charge recombination. So you're losing your photons because your charges recombine and the light just gets re-emitted. And the final challenge is choosing the right band gap. If your band gap is really large, you should have a lot of driving force for your reaction to occur. So reactions should be very fast and can compete with recombination, which is great. But then if your band gap is really large, there isn't very much light around in the solar spectrum that can drive your photocatalyst. If you take a really small band gap, there's loads of light available to drive the photocatalyst because you can now use visible light. But the reaction, because it has almost no driving force, is going to be very slow and might be outcompeted by charge recombination, so you don't get very much product. So basically, either way you do it, it's not working. That's the big challenge of photocatalysis. But there are a few tricks to circumvent this. First of all, we have to measure the efficiency. So the efficiency, again, solar to hydrogen efficiency. Now actually I spelled it out. So it would be output energy divided by incident energy. In this case, is the moles of hydrogen produced per time times the energy of the hydrogen when you combust it, divided by the light intensity and the area of your photocatalytic material. This takes into account the energy of the light and the intensity and everything. Another measure is the quantum efficiency. That only takes into account the number of photons, not their energy. It's like the Faradaic efficiency doesn't take into account the voltage you're applying, only counts the number of electrons, and so does the quantum efficiency only count the number of photons. There's two types in which to calculate the quantum efficiency. One is the internal quantum efficiency, or IQE. It's the number of reacted photons divided by the number of absorbed photons. So basically tells you how much of the light that I'm absorbing is actually used to generate fuel. So if the charges recombine, they don't create fuel, so the efficiency goes down. So it's a good measure to give you information about recombination or side reactions, such as back reaction or anything else that could happen. The other type of quantum efficiency is the external quantum efficiency. So this takes into account not only the absorbed photons, but all incident photons. So it's a superposition of the internal quantum yield and the light absorption. So if all the light is absorbed, your internal and external quantum efficiency will be the same. If some light isn't absorbed, your external quantum efficiency is going to be lower than the internal quantum efficiency. But it's normally useful to determine both at the same time to give you a good picture of the limitations of a photocatalyst. Addressing these challenges. So we can do some things to kind of circumvent this. One way to suppress charge recombination is by building heterojunctions. A heterojunction is a junction of two different semiconductors, and in a type 2 heterojunction, they are aligned in a way that both the conduction band and the valence band of one semiconductor are at a higher potential or more negative potential than the conduction band and valence band of a second semiconductor. If you excite both of these semiconductors, you get charges from the valence band into the conduction band on both sides. But because of the band alignment, electrons in the higher lying conduction band will drop down to the lower lying conduction band, and electrons from the higher valence band will drop down to the lower valence band, which in turn means that holes from the lower valence band will go up to a higher valence band. So overall, what happens is the holes will accumulate in the valence band of semiconductor 1, and the electrons will accumulate in the conduction band of semiconductor 2. So you are spatially separating the two charge carriers, which then prevents recombination. So you get a higher efficiency, but because this conduction band is lower than that, and this valence band is higher than that, the overall potential difference between those two bands is smaller than the energy used to excite the semiconductors, so you are losing some energy, very similar to what happens in natural photosynthesis. Another way to achieve a similar outcome is using a dye-sensitized photocatalyst. In this case, using a molecular dye or often an organic dye that absorbs visible light. You excite it, and electrons from the LUMO then inject into the conduction band of your semiconductor. The semiconductor normally has a large band gap, so you don't actually excite that. So you are only using it as a medium to kind of carry charges. So again, the excited electrons are now on one material, whereas the holes are in a different place. So you are spatially separating electrons and holes, so you are preventing charge recombination. But the holes are now on the HOMO of your dye, which means it's not very oxidizing, so water oxidation will be very difficult, if not impossible process in these kind of systems. So again, you are losing potential difference because the conduction band where the electrons are and the hole where the holes are very close together now, so you don't have much driving force for water splitting. So there's some challenges to work on. One way to overcome this problem is by doing a Z scheme, very much inspired by nature, and where you have two light absorbers now working in tandem rather than in parallel. So you have one photocatalyst, which I call the oxidation photocatalyst, where you excite electrons from the valence band to the conduction band. And then the electrons from the conduction band reduce a mediator, which then reduces the valence band of the second photocatalyst, or transfers electron to the second photocatalyst, where the electrons get excited again into that conduction band. So what you've done now is you've done a spatial charge separation of electrons and holes across two different materials, separated by a mediator, so spatially separated, very much like PS1 and PS2. Plus, you've got two excitations of one electron, so you have a Z scheme. So the overall potential difference of those two steps is additive. So you have a fairly high potential difference between where your holes and your electrons are. So you're likely to get a very good driving force for water splitting. So the system should be rapid and very efficient in terms of preventing recombination. The problem, of course, is that now these systems become quite complex, and you have to make sure all the components match up really well for this to work well. So you are now adding complexity to the system. So it's never really right, whatever you do. And finally, the last issue, as I said, is the reverse reactions. So when you form water and, if you split water and form hydrogen oxygen in the same compartment, you obviously have the chance these recombine, so you just form water again, or oxygen is just directly reduced on your cathode to form O2-, and then taking away electrons and potentially also destroying the catalyst. That is a problem because oxygen reduction is very easy, kinetically and thermodynamically, and so this is a huge competition in photocatalysis. There are a few things you can do to prevent this. One is you can just evacuate your cell, you can just pump off any oxygen, hydrogen continuously, which then obviously solves the problem, but then continuously pumping on the cell costs a lot of energy, so it makes the process overall not very energy efficient. Instead, what you could do is you can take a catalyst that is selective, it only releases protons and not oxygen. Those catalysts don't really exist at the moment, although some people are working on it. But finally, what you can do, what has been done quite successfully, is to introduce selective blocking layers. So you coat your hydrogen evolution catalyst, in this case here a rhodium particle, with a layer of chromium oxide, and this chromium oxide is good at letting protons diffuse through it, so they can get reduced to hydrogen, but it's very bad for the diffusion of oxygen. So oxygen doesn't diffuse through the shell, and so oxygen doesn't reach the rhodium, so oxygen is not being reduced, the whole system works quite well under oxygen, which then solves your selectivity problem. That's everything from my side. That's all you need to know for the exam. I advise you strongly to go through the workshop questions and the practice exam question that I put up on Blackboard. If you have any questions about these things or anything from the lecture, feel free to drop me an email. We can chat over Zoom if you want to address any of your questions. Good luck and hope to see you soon.